So today we are going to look at compactness in a topological space. What does it mean for a topological space to be compact? For a topological space to be compact. So we are going to first define what a cover is. So let X be a set. If I have a set X, what is a cover of X? Definition. So we are going to first define a cover of set X. So a covering definition. A covering of set X is a collection of subsets of X whose union, collection of subsets of X whose union is the whole of X. Collection of subsets of X whose union is the whole of X. So that is a covering. Then we can define an open cover. An open cover of set X. So this is a collection of open subsets of X whose union is the whole of X. Is the whole of X whose union is the whole. That is an open cover. For it, it's just a collection of open subsets of X whose union is the whole of X. So in this case, X is equal to the union. X is equal to the union of sets U, whereby these sets are coming from that collection. So this symbol, which I can call the curl symbol, so this is representing the collection of those sets. So now X is just the union of those sets picked from the collection of subsets of X. So in this case, this symbol is representing the collection. It's the collection of open subsets. Collection of open subsets U of X. So X is just simply the union of those sets. X is simply the union of those X. Now let us look at some examples. Part A. This set here, the set, let me call it n plus maybe 1, where n is I can call n I can put negative n here, negative n there, then call n a natural number. This set forms a cover of the real numbers. Yes. So this is a collection of subsets of R, whose union is the all of R. That is just an arbitrary. Uh, it's it's an arbitrary cover. Yes, an arbitrary cover. We can also have this. It's not an open cover because these sets are not open. Yeah, it's not an open cover. We can also have z, z plus 2, where z is an integer. This forms a cover of R. That one also forms a cover of R. Then which other one? We can look at an open cover. An open cover of R, collection of open subsets of R. We can look at this z plus 1, where z is an integer. Now this forms an open cover of R. It's a collection of open subsets of R whose union is the all of R. So those are some of the examples. Now we can now define compactness of a topological space. So definition: let X tau be a topological space. Let that be a topological space. Now X, that space is compact. Is compact if every open cover of X is compact if every open cover of X has a finite subcover. X is compact if every open cover of X has a finite subcover of X. So what does this mean? This means that every open cover should have a finite subset that still covers X. Yeah. X is compact if every open cover of X has a finite subcover, as in that open cover should still contain another collection which we are calling a subcover, which still covers the whole of X. Every open cover of X has a finite subcover, has a finite collection of open subsets of X, has a finite collection of open subsets of X which still cover the whole of X, So we are going to look at some examples. Some examples of this compactness. So examples, part A, R with the usual topology is not compact. R with the usual topology is not compact. The usual topology is just a collection of open intervals. Yes, yeah. So whenever we are discussing about the usual topology, we just mean the collection of open intervals. Yeah. So R with the usual topology is not compact. So how can we demonstrate this? Because we say that a space is compact if every open cover of a set X has a finite subcover. So we need to construct an open cover of X without an open cover of R without a finite subcover. So how are we going to construct that? So we are going to let where n is a natural number, let this be an arbitrary open cover. Let this be an arbitrary open cover of R. So we are going to construct, we are going to show that if that is an arbitrary open cover of R, it has no finite subcover. So what if we assume by contradiction that there exists a finite subcover? So suppose by contradiction, suppose that there exists a finite, suppose by contradiction that there exists a finite subcover, that there exists a finite subcover, this one, comma, negative n2 up to negative nk of R. Suppose by contradiction that there exists a finite subcover, there exists a collection of finite subsets, finite open subsets of R which still cover the whole of R. So by contradiction, if we have that finite subcover, let us try to compute the union of the whole of those sets and see whether we shall come up with R. Let us compute the union. So we want the union of these sets. We want to collect the union of those sets. Maybe I can call this collection, let beta represent this collection. N1 up to negative nk. I want to compute the union of those sets. The union of those sets. So I'm going to let M be the maximum of N1, N2 up to Nk. After Nk. After Nk. M is just the maximum of those n's. The maximum of those n's. So let us try to get the union and see what will result. So now the union of these sets, the union of sets U, whereby these sets are coming from the collection beta. The union of those sets. The union of those sets is actually, because these are finite sets. We can take a simple example of negative 1, 1, negative 2, 2, negative 3, 3. Look at that collection as simply that one. It's a collection of finite sets, finite open intervals. Now, what happens if you try to compute the union of that, the union of this collection? You realize that if I'm to compute the union here, that union will actually be this set, because within this set we have this embedded here, also this is embedded there. So that's why I had to let M to be the maximum of these N1s, N2, N3. So actually you realize that this union is going to result into negative M and M, and this is not equal to the whole set of R. So R is not compact. R is not compact. Now we can look at another example. We can look at another example. So you just look at this collection as something which looks like this. Try to compute the union, you get that. So another example of a space which is not compact. So the interval this one is not compact. It's not compact. So we want to prove that that interval is not compact. So we are going to do that by the same way, because the space is compact. Because if the space is compact, if every open cover of that set has a finite subcover, it's not compact with the usual topology. Not compact with the usual topology on R. So we have to construct an arbitrary open cover and show that it has, we have to come up with an open cover and show that it has no finite subcover. So we are going to let let 1 over n, where n is a natural number. This is an open cover of this interval. This is a collection of subsets whose union is the all of that. So that is an open cover of that interval. So we have to show that that open cover has no finite subcover. So we are going to suppose to the contrary, assume that there exists a finite subcover. Assume that there exists a finite subcover, which I can call beta. So this beta is a collection of 1 over n1, 1 over n2, 1 up to 1 over nk 1. That is beta. Now we are going to let m be the maximum. This the maximum of n1, n2 up to nk. Then try to compute. We are assuming that, to the contrary, we are assuming that that set has a finite subcover of the interval 0, 1, and we are letting that to be our finite subcover. Let us try to compute the union of these sets. So the union of sets U, which sets are coming from beta, this is actually equal to 1 over m 1, and this is not equal to 0, 1, 0, 1. You can still take an example of just as we did in the first case. Now this beta is representing sets of this form. By the way, also what I need to stress is that this natural number is starting from n equals 2, 3, yeah. N is a natural number starting from n equals 2, 3, yeah. Because if n is 1, then I'll have 1. I'll have 1 as I'll have 1 standing on its own. Yes. So if I start with n equals 2, I'll come up with sets of this form: 1 over 2, 1, then 1 over 3, 1, in that order. If we try to get the union of these sets, the union of these sets will actually be this interval. Yes, will be this interval. But if we include 1, for example, if we start with n equals 1, we shall have this set, this singleton as a separate set here. So that's why we need to start from n equals 2. So I was still telling you that you should look at this sub collection, this finite collection, as consisting of 1 over 2, 1, 1 over 3, 1, maybe up to 1 over, because it's a finite subcover. It's a finite subcover. So they are finite sets for up to 1. Now try to compute the union of these sets. The union of these sets will actually be this set here. Because look at this. Let us try to convince ourselves. 1 over 2, that is 0.5, 1. Then 1 over 3, that is 0.3, 1. And then this is a quarter is 0.25, 1. So you realize that this interval here is in here. Also this one is in there. So actually the union of these sets will result into such a set which is not equal to that interval. So that is an introduction to compactness in a topological space.